Well, I think we can get started. Welcome back, folks. We're about to finish off our second week, and for our major thing to work on today, we're going to run through section 7.2, finishing it off. So this one's going to be due a week away, January 30th. And then we should be able to make some decent head segue into the section 7.3, trigonometric substitutions. This one is like a more advanced version of what's going on in section 7.2. They are still a type of U substitution. Our author mentions it's a type of inverse substitution. We'll see what's going on with that when we get going. But much like in a lot of these problems, when we make the right substitution and put them back in together, it all starts to come together in the same sort of way, just a different start on this one. Also, SOHCAHTOA makes a comeback in section 7.3. So right angle trigonometry is part of the technique on this one. So a good opportunity to look at that again, dust off some of our skills on trigonometry with that. Well, section 7.1 is due today, and I guess at that point, I'm pretty much out of announcements. Any questions at all, folks, to start us out? Okay, I do want to mention that one question you are all allowed to ask at any time is, if you're running through a homework assignment and something just seems like really wild, maybe it feels like we didn't cover it in class, or you're just not sure how to start it, that's absolutely a question you can ask at the start of class. I'll be very happy to look at it. So again, if there's a homework problem that just seems weird that might be a good one to share with the class, don't hesitate to throw it out there. Yeah, go ahead. Oh no, I'm gonna have to get into that and fix that right away. Did I put in anything there? Gotcha. Yeah, that's my mistake on that one. I'll get that fixed right away. Thanks for mentioning it. Usually when I try to fix something, this is what I'm supposed to do. Otherwise, I'm never going to remember this on my own. I need a file that says, let's go all caps. Reminder. All right, that's how I'm definitely going to take care of that. And my goal is to put in the PDF for all those sections. So thank you for mentioning that again. We should be about here. Include problems and solutions in 7.3. Okay, I'll get working on that one. So again, just as a reminder, especially if you just joined the class recently, the add drop date is next Monday. For each one of our homework assignments, even if you're working out of an older textbook, you're probably fine. Just click on section 7.2, and this is what is supposed to happen. It should have the PDF of the actual problems in the edition.
Unless you're in a relationship, that's fine.
To open mic. So let's click on 7.2. And these are the actual homework assignments. I forgot to do that in 7.3, so I'll get those uploaded shortly. But other questions at the moment? Okay, well, let's jump into 7.2. Here's where we left off. The diagram above is a great unit circle diagram for taking on problems like these. There's a couple in this homework set where the major feature of this problem wasn't so much doing the integral. It did have a cool trick where we need a trigonometric identity to get to here. But this problem is more about this step right here. We have to do our trig evaluations when they come up. But think of it as just an opportunity to brush off on your trigonometry skills, because this kind of stuff just never goes away, especially if you're taking more math classes, more engineering classes, and so on. So let's start our work today on this thing here. Tangent cubed 3x, secant power 5 3x. We need a good substitution to start this one out. And if something doesn't pop out at you right away, sometimes the best thing to do is just try something. So let's leave it up to the class. Any volunteers for a good U substitution on this one? Yeah, if we have an odd power secant, that's a really great choice. It's also the highest power that appears there, so that says excellent choice with secant. Because this one is odd, we definitely need to use secant on this one. So let's go U equals secant 3x. We're using just power 1 on that. Very next operation we need is a differential. So take du. It's going to be secant times tangent. So this is the structure. I put a little bit of space in front because now the chain rule gets involved. 3x goes into all those positions. Then we must multiply by the derivative of 3x, which is 3. I usually just put that way out in front, just sort of looks better. And then dx to finalize the differential statement. Once we run through this, we have to decide, is it going to work? Here, we're going to have u power 5. Well, let's think about it again. You have to give away a power secant and a power tangent. This drops down to power 4. This drops down to power 2. But that's good if it's tangent squared, because identity is going to help us through that portion. So that tells us we're on the right track. Let's start dropping the powers on here because of that differential. This is now tangent squared 3x. Let me make sure I don't write too small. Tangent squared 3x, secant power 4 3x. And I'm just going to go times, not that you have to put a bullet there, but this is just me organizing in the integrand. Everything to the right of the multiplication dot is now going into the differential equation, which is tangent 3x, secant 3x, dx. Let me just partition that away. Here we do a check to see if we really are on the right track. So this part right here, secant power 4, turns into u power 4, so that helps us out. Tangent 3x, secant 3x, dx. All of that is just another way to say du. Oh, good point on that one. I missed that 3 right there. Usually what we would do here is either multiply by 3 over 3 in the integrand or divide out that 3. Good catch on that one. So let me write it in this way. This is our author's typical approach. A third du is secant 3x, tangent 3x, dx. And then that means my little description here where we wrote du, it's really going to come in as a third du above. The only thing left over is this portion, the tangent squared. But that's just where the trigonometric identity gets involved. Let's write out tangent squared 3x becomes secant squared 3x. You can see the identities above in the notes or the associated document in Moodle for more trigonometric identities. Go -1. And we have a value we can put right there now. This turns into u squared -1. And all that right there gets thrown in for the tangent squared 3x. Let me put in this pencil just to describe it as before. So u squared -1 goes into that location. So if we can describe everything in terms of u and du in our integrand, then that tells us our u substitution here will be successful. Any questions so far, folks, to this stage? Okay, although this stage right here, it's purely organizational, it's a really good idea to try this out. It's going to help you in the homework, and if you get in this kind of habit, it makes you more robust in getting through this kind of problem once it's now in an exam situation. You're just going to be practically dealing with your muscle memory and how it all comes together if you show this detail each and every time. You'll get to the point where you might skip more steps because you just are anticipating those steps. But writing them all out the first time is how we get there. So let's drop this all in. In this position, we've got u squared -1, highlighted in yellow again just to show where it came from. From here, it's u power 4. And from here, we have times 1/3 du. So that whole tangent 3x secant 3x, even though it's in a different order here, is the same exact thing. So that's a fantastic integral. I usually put my 1/3 out in front. I just forgot to put in that extra space. So I'll do it now at this step. We need to bring these together. So this is now u power 6 minus u power 4 du. And from here on out, we've got a calculus 1 integral. This is a pretty fast one to solve. We'll write down 1/3. From here, we have u power 7. And from here, minus 1/5, u power 5. Constant of integration has to be thrown in. It's super easy to forget. So we pretty much mention it each time when we're starting out. Then last thing to do is just undo our substitution. In place of those two variables u, we're just going back to secant 3x. So from here out, we're pretty much just writing down as fast as our hand can move. A third, secant power 7, 3x, minus a fifth, secant power 5, 3x. Add in our arbitrary constant, and we've got it, folks. That's the antiderivative of that mess there. Yeah, go ahead.
First fraction.
That is a weird copy error. Thank you for spotting that. Yeah, that should have been a 1/7 right there. I mean,
Besides the u6 minus 4, is u to the 4th at all, maybe u squared? Or does it not work like that in like that stuff, yeah?
well, you could factor out u power 4 to get the u squared minus 1, but the trouble there is the antiderivative is harder when those two functions are multiplied together.
Yeah, we distributed it, so it's u6 minus u to the 4th. Could we just make that, simplify that to u squared?
The u4th right here?
Yeah,
Oh, I see what you're saying. Unfortunately, these would be considered unlike terms, so they wouldn't combine in that kind of way, changing the power. If we had something more like this, say, for example, something like 6u power 6 minus 7u power 6, we could combine these, but only because the exponents are the same. That forces these to be like terms for still the same power, u power 6. Other questions at the moment? Yeah.
Did you make the tangent in front of the sine or the cosine, and then turn the secant into one with cosine and do it like that?
Yeah, sometimes that does work out. And if you notice that up here, way up here, hang on, even further, that's basically what we did on this one. We don't really have a guidance on how to handle cotangent against cosine, so we just rewrote the whole thing. But the thing that's kind of tricky about that is your mileage can kind of vary on this. Let's take a look at what would happen in this problem. So let's call this method 2. I have no guarantee that I'm going to be successful in method 2, but it's always a worthy try. Sometimes these do simplify in a huge way that can sideline a lot of this different work, or maybe it's a different u substitution, but just more approachable. So let's come down here. So same problem as before, but we're trying it in a different direction. Let's say for method 2, re-express the integrand in terms of sines and cosines. I guess that's not a valid way to say that. There we go. So going back to the integrand, like you said, tangent cubed 3x is just sine cubed over cosine cubed. Let me just start from this direction. Secant power 5 3x. So this will turn into sine cubed 3x divided by cosine cubed 3x. The secant power 5 now turns into 1 over cosine power 5 of 3x. So this is now sine cubed 3x, cosine power 8 3x. Let's try integrating this one right here. So tangent cubed 3x, secant power 5 3x dx can also be now attacked from the direction of integrate instead sine cubed 3x divide by cosine powered 8 of 3x dx. So now a u substitution here could be tricky. Any volunteers for a choice on a u? Let's give it a try. So if u equals cosine 3x, next step was going to be that differential. Du is going to be equal to, this will turn into a negative, I'll put in some space, sine 3x. Differentiate 3x through the chain rule, and the 3 would go here with the dx. And now that we have a sine, we'd be giving away one power of sine here, leaving sine squared. I think this will actually work. Should we finish it off just to see what the next steps would look like? You might as well. I mean, it's just another u substitution, right? I think that's a cool suggestion as well, because it tells us you don't have to go to our author strategy. If you find a new way that works, go for it. Looks like this is going to pay off. So this is turning into, because we have, well, let me do that extra step that I seem to be forgetting today. They're going to divide out that -3. -1/3 du equals sine 3x dx. So because of this extra factor of sine, we lose one from here and call it sine squared of 3x cosine power 8 to 3x, and go times, we've got sine 3x dx going over here. So from that, we're going to put in -1/3 du. Sine squared of 3x is just through an identity. Down below, this is just going to now be a u power 8. So that's looking good. And just a standard attack on the sine squared, we write out sine squared 3x is 1 minus cosine squared 3x. Then that involves u all of a sudden. So now we've got 1 minus u squared. So all that will go up here in the numerator. Let's see how this finally all ties together. So this is now integrate this -1/3, I'll put out in front. For the sine squared, we've got the function 1 minus u squared. Down below, u power 8. And sine 3x dx is the du with the -1/3 now way out in front. This looks very approachable now. At this stage, we can now, instead of multiply, we're just dividing by u power 8. So -1/3 integrate 1 over u power of 8 minus u squared over u power 8 du. Now this is the division step. Well, here I'm just changing the exponent, bringing the base up to the numerator for u power -8. And same on this one. This will turn into u power -6. On this one, you can visualize it by either taking 2, subtracting the power 8. I think that's a standard way algebraically. But usually I visualize it this way. U squared over u power 8 is 1 over u power 6, or we're just bringing it up into the numerator, so it's written this way. Then du goes in, and now we're ready for an antiderivative. Any questions to this stage, folks, for this new approach? Okay, to finalize this one off, let's write this as -1/3. Antiderivative here is going to be power goes up by 1, so -1/7, u power -7. Same on this one. This will be +1/5, u power -5. So we have an extra sign swap in this involved. And finally, add a constant, undo our original substitution. I forgot it's cosine. So cosine is going to go into those positions and we'll have a result. But let's compare what we did above here. We had secant power 7, secant power 5. We have cosine power -7. That is, in fact, a secant. Cosine power -5 is, in fact, secant power -5 as well. So that's kind of cool. Not always do the results match up. A lot of times, if you pick a separate method or different approach, you get a algebraically equivalent antiderivative as your end result. But this one was nice and matched up directly. So we've got -1/3, -1/7. I'll leave it just as a cosine function, cosine 3x. Putting the power on the outside in this one, just for clarity, there's, like we mentioned before, a chance for a misinterpretation with a negative exponent. +1/5 cosine 3x power -5 plus a constant. So that's an equally a valid approach. I like this approach because it's just using ordinary u substitution between sines and cosines. That's the first concept in these notes. The only difference is you have to go through the trigonometric simplification here, but really that's not too much to worry about. So I'd say pick your poison when it comes to these exercises. If you find an approach that works, then just go for it. You don't have to follow the author's approach directly each and every time. Any other questions, folks, with dealing with this integral here? Kind of hard to zoom out sometimes on these. Okay, well, we have just one more for this section's notes. Then we're going to move over to section 7.3. So here's the last one of 7.2. As promised, this one is different from all of the rest, but that's good in a way because you don't want to forget how section 7.1 goes when you're in section 7.5, for example. It's good to kind of inject the old problems into the new ones as we go. It's in some sense definitely a trigonometric integral because there's a trig function, but we're going to use integration by parts because we have an algebraic function multiplying the trig function on this situation. The acronym we often use is the LI, hang on, what am I doing here? Okay, it was deleting after I wrote it down the first time. LIATE to stand for logarithmic, inverse, algebraic, then trigonometric and exponential. Again, this acronym is helpful for us because the A here says U ought to be the X. Probably you already guessed that. It's usually a good choice for your U in integration part by parts whenever X comes up. Then dV is all the rest. So let's set dV to secant squared x dx. Next thing you need to do is complete this table here. On the first column, it's the differential, du equals dx. The second column is sometimes the trickiest, but the reminder is, whatever v is the antiderivative of what you said dv was in the first place. So back over here, we need antiderivative of secant squared, but that's just going to be tangent, since derivative of tangent is secant squared. Finally, we put it all together just by writing down the structure for integration by parts. If you're using this table, it's a good idea to now say the integral is equal to uv minus the integral of v du. Because now you have 1, 2, 3, 4 placeholders. You're just plugging in information at this stage. That's a lot of mathematics. Write out a structure, organize it, and then just do a huge amount of substitutions to move through the problem. It's basically what we've been doing all semester so far. So for u, showing up here, v and du, we've got x times tangent x, subtract the integral of tangent x. For du, we just throw in a dx, which gives us the full information for the antiderivative here. Here's where we need to dig a little bit deeper. This becomes x tangent x. And I totally understand if you forgot the antiderivative of tangent x right here. We can solve it by writing this as sine over cosine, use integration, use substitution to come up with the result. But that's reinventing the wheel. This is an integral that comes up a lot, so if you know the answer, you just want to cite it. Anyone happen to recall how it goes? As a hint, there's a natural logarithm out of nowhere. Good call, negative natural log secant x. Again, these are easy to forget, so if this seems like a little foggy, go up to the very top of these notes. Takes a while to actually scroll up there. And we're using this result right here, natural log secant x. This one's natural log sine x, which looks a little bit weird, but that's because there's actually a negative sign that was in front here that used properties of logarithms to turn it a cosine into a secant. So way back to the bottom. Oh, I guess we're done. That's the whole problem. You gotta love integration by parts. When it works well, there's not too much to say, so it's a great technique. Any other questions, folks, on getting through this one? Okay, so that's our trigonometric integrals. Really, all section 7.2 was a bunch of u substitutions and lots of trigonometric identities that we were working on. Section 7.3 is similar, but one slight little difference on how we form our substitution. So let's take a look at that in our next section. So now we're working through section 7.3. I don't intend to finish this one today. That would be cruel and unusual. So what you'll notice when we come back next week is this whole file and assignment just gets moved down a week. So things are kind of in dynamic flux as we move through the documents. So we're on 7.3. And in 7.3, this table right here is fantastic. This is going to be included on our exam 1, along with other results. And I'll just be sharing that file very shortly so you can start planning on how to study. But this is one of the nicest tables ever because it tells you the problem in your integral. This is the whole reason why you want a trigonometric substitution. It tells you the substitution you should make, the domain where it's valid, and the related identity you're almost certainly going to use when you use this technique. There's 3 different things we're kind of trying to work with through here. They're all square root functions, and these are sometimes pretty tough antiderivatives to come up with. Sometimes you can make a u substitution work, but it can take a lot of ingenuity, and other times it just falls on its face. You really need one of these ideas. So another way to look at this table is these expressions right here are things that are inside the integrand. We don't mean it's the whole integrand. We just mean it's a factor, or maybe in the numerator or in the denominator. For example, that portion right there indicates trigonometric substitution might be a good choice. A u substitution is tricky because the differential of 1 minus x squared involves a negative x, and we're up to x cubed. So that's telling us this might be more straightforward by not using u substitution at this stage. Other elements here are the way we form this depends on where the variable is. If we have a minus x squared, well, that's a minus sign squared being involved for that identity, so we use that. For plus, that should remind you of the 1 plus tangent squared. And for x squared, that should remind you of secant squared minus a value. So the format of the expressions are matching up with the identities. Making that connection there really helps out on choosing which is which. And last takeaway here is, whatever this value is, we go to here by just taking the square root. So that's our setup for the trigonometric substitutions. Because this table is so valuable, I want to take a version that's not been modified and plug it down here on our next problems as well. When you're doing these kinds of problems, it's always good to be looking at this kind of table until we feel so confident that we just don't need it anymore. That's a good place to be, and you're prepared for exam 1 material on this at that point. So let's give this a try. First thing we have to do is decide which of the 3 expressions is most similar. Usually you're just looking at where x is. If we have x to the right with a negative sign attached, we're on row 1 of this table. That means x is going to be equal to a sine theta. A comes from this value, and we take the square root of it. But if it's just a 1, there's no need to put a 1 here any longer. We'll just write sine theta. So that's our x. This is a different kind of substitution in a real sense because there's no portion in here that's a sine theta. So this is definitely a whole new technique in a certain sense. But we still do exactly what you would have done in a u substitution. After you form x, you need to compute very next dx, the differential. So here's our differential dx. Take the derivative of sine, which is cosine, and then d theta, because the variable itself happens to be theta as well. So we now have something for dx, but this time we're replacing just dx with all of that right here, cosine theta d theta. Now, for x cubed, that's just going to be sine cubed, so that one is not as bad to deal with. The one we need a little bit more work on that needs the identity is the portion with the square root right here. So let's do that on the margin as well. It is root 1 minus x squared equals root. The x squared here is a particular substitution. That just turns into sine squared. So go 1 minus sine squared theta. Once you get to this stage, here's the identity that's involved. 1 minus sine squared theta is just cosine squared theta. So this turns into square root cosine squared theta. And here's where we have to be actually pretty careful. Unless you knew you're working in a specific domain, these domains right here. The trouble over here is that the square root of anything squared is the absolute value of that thing, and we can't get away from that fact. But notice this domain. That's highly specific between negative pi over 2 and positive pi over 2. We plot that out. It would look like this. Go negative pi over 2 up to positive pi over 2. The highlighted portion right here is the relevant domain. Now pick any angle whatsoever in this domain. Let's say it's this angle. That's our theta. Because we're concerned about taking the square root of cosine, we need to know if it's positive or negative. But cosine is this value right here on the positive end of the x-axis. So that says, even if you were really careful and wrote absolute value of cosine theta, by the way, good on you, that's the right value. We are using this domain to say absolute value of cosine theta is cosine theta in the first place. So in all of these problems, absolute value falls off because the domain has been carefully targeted to make this work out algebraically. Doesn't matter where angle theta was. If it was, say, way over here, I'll call that theta 1 just to differentiate it from the other. Cosine is still this value. It's still a positive quantity. So that whole thing highlighted in yellow back in our integrand just becomes cosine theta itself. But there is more now. One trouble with our integral is it's a definite integral. There's a huge difference about how you approach this on the definite versus indefinite. The indefinite one is where we need to use SOHCAHTOA. That's us undoing the substitution. But if it's definite, probably the best technique here is change the limits of integration. That way you don't have to undo the trigonometric substitution here, which is harder to do than undoing a u substitution. So let me scroll down to the next set of steps. Any questions first, folks, with the 3 components listed out here? Okay, so starting with the variable x. Let's write this out very carefully. X goes from 0 to 1. But you want to keep the format really, really familiar, not changing the order. So make it the lower limit 0, upper limit 1, matching the order limits were written out here. You take these values and you plug them into this equation. Now it's starting to feel different, right? Because usually x would be right here. It is not. This is an inverse substitution. It goes on the opposite end of the equation. So we have 1 equals sine theta. That's a trigonometric equation we have to solve out of nowhere. And the next one is 0 equals sine theta. Our second trigonometric equation to solve. Once we solve those two, we'll have a value for theta on the upper limit and a value for theta on the lower limit. Anyone happen to know the solutions to either one of these? Absolutely. Pi over 2 on the top. That's just because sine of pi over 2 is exactly 1, so that solves this one. On the bottom, sine of 0 is 0, so that solves the lower one. So we have direct and exact values. Those are going to change the limits of integration up here. So now we're ready to get started. Putting all of this together on our right column, we can transform the integral into something a lot more trackable. So here's how it goes. It's now equal to a definite integral. Come back over here. We're going from 0 to pi over 2. Next thing is the x cubed portion. From that, you come over here, we're just putting in sine cubed theta. The portion that's the square root. Again, the qualities, writing out things very carefully helps out. This is more about organization in some sense. That turns into cosine theta. And, oh, didn't mean to do that. Let me try again. And last is dx. Dx itself turns into all of this stuff, cosine theta d theta. And this is our integral to handle. Notice what it's done. It's taken a rather nasty integral right here. This is the section 7.3 problem. We have now reduced it to section 7.2. It's an ordinary trigonometric integral in that section. So now section 7.2 style of the question. Let's simplify it down and start working with it further. We're going from 0 to pi over 2 on sine cubed cosine squared. So now here's the reason why we changed the limits of integration. That section 7.2 problem we're looking at right here is a whole new substitution. This one's the ordinary u substitution. So we have to come back over here and come up with that brand new substitution. Changing the limits of integration as you go takes it so we don't have to do all the tedious work of undoing every single substitution that comes up. Sometimes it can be quite a lot of them. Usually no more than 3 in one problem. That would be already a pretty outrageously long problem. We're doing 2 substitutions on this one. So now, let's pick a substitution. Our strategy for sines and cosines are find the odd power. If it exists, there it is. Pick the opposite function to power 1. So it suggests u equals cosine theta should do the job. Let's check it out by considering the differential. It's negative sine theta d theta. I'm going to remember this time to move the negative sign over. So negative du is sine theta d theta. And next thing we could do is, again, change the limits of integration. But this time it's a little bit easier. It's not a multi-stage process where you're solving an equation in the middle. It's a normal thing we're used to doing. So start right here. From 0 to pi over 2 is the variable theta. So say from theta at upper limit pi over 2, theta at lower limit 0, it's now transformed using u. This time it's normal. But let me emphasize that one more time because this can really kind of hurt your brain when you're not expecting it. In a trigonometric substitution, the value 1 went here, and we had to solve an equation. But in a u substitution, the value pi over 2 goes here. This is just an evaluation, not an equation we solve. It's in this way we consider the trigonometric substitution to be an inverse substitution. So let's keep on running through it. Pi over 2 goes inside here for cosine. So we have u equals cosine pi over 2. But cosine at pi over 2 is 0. Lower limit, we have cosine at 0. But cosine of 0 is exactly 1. And notice how weird that looks like. Our upper limit is really 0. Our lower limit is really 1. But when I go to put this back into the integral, I am extremely tempted to put 1 as the upper limit of integration, 0 is the lower limit. But keep things in order and organized, and you won't make that easy to make a mistake. This really goes from 0 to 1 as awkward as it feels. The next thing we have, a bunch of other stuff we have to do. We have the cosine here. Let me back off by 1 step and just write out the next things we would do to handle this substitution. Kind of got excited on changing the limits of integration here. Typically in this u substitution, because we saw a sign of the differential du, we would come back over here and rewrite sine squared theta, cosine squared theta times sine theta d theta. So we give away a factor of sine theta. And now all of this right here, as per that equation, is negative du. Next, this part is the easy part. That's the u squared. And this is the part that uses the trig identity. Again, it's the same identity that's up here. I think we've used this identity maybe 5 or 6 times so far. I'm losing track. But let's rewrite it out. Sine squared theta becomes 1 minus cosine squared theta, which then becomes, because of our substitution, a 1 minus u squared. And that's the portion that's going to be dropped in right here. I haven't changed the limits of integration, so it's still from 0 to pi over 2. Okay, now we're ready to put in the new limits of integration. Now that everything is all set up and ready to go, we're integrating from looking to here, from lower limit of 1, upper limit of 0. On this portion, we just have a 1 minus u squared. Again, it almost feels like deja vu. Then it's multiplied by u squared. Sine theta d theta, we'll throw in the negative out here, and du goes into this location. So the pretty complex integral has now been transformed down into this one. This is our whole goal in chapter 7. It's become a calculus 1 integral. But it is still tricky because the limits of integration are strange looking. If you want, you can absolutely fix that. Anyone recall the trick to make this better? Good call. As folks are saying in class, if you change the limits of integration, you just multiply by -1. I think that's a really good strategy on this one because that's kind of hurtful for our mind to look at that. And we're also deleting the negative sign. You might as well reduce the complexity in that way. So now we're integrating from positive 0 to 1. Distributing through, we have u squared minus u power 4 du, and we're on our way. Next step is that this is 1/3 u cubed minus 1/5 u power 5. That entire expression will be evaluated from 0 to 1. And notice, this is the reason our author always changes his limits of integration almost exclusively in the textbook, because if you have to undo the u substitution and then undo the trig substitution, this problem is actually a lot more technical and tougher to get through. So I encourage you try it this way. If you're not too happy with undoing substitutions, it really helps out. All we need now to do is throw in 1 for the upper limit. You would just get 1/3 minus 1/5, subtract 0 for the upper limit. That's just going to give us 1/3 times 0 minus 1/5 times 0. Really, you don't have to write in that at all. We know it's 0. This is more just a paper trail in the notes. So it's just 1/3 minus 1/5. It's tempting to add these together. You can go 3 by 5, 5 minus 3. So all I've done is multiply by 5 over 5 here, multiply by 3 over 3 here, and we get 2/15 out of nowhere. So the claim now is the area under the curve of that function is exactly 2/15, the net area altogether. You know, that looks like this function is a positive one, so this would be all positive area altogether. But any questions at all, folks, on this approach? Okay, it really is a long problem. That's, to me, the thing that's really different in Calculus 2 over Calculus 1. Problems out of nowhere just get really, really long. But if you break this down into chunks, a trig substitution section, a u substitution section, organize your work carefully, it does come together in a nice way. Well, let's try it out again for the next problem, where we're going to handle this integral. Doesn't look like it should be terrible, but the presence of this square root and the fact that x squared is in the denominator to power 2 means u substitution on this one probably isn't easy either. It could take an extreme amount of ingenuity and creativity, but we'll just practice it this way because this is the thing to try as well. What I'm mentioning with the u substitutions is if you find a u substitution that does work and you'd rather use it over the trig substitution, you are welcome to do so. So anything that does work will qualify for full credit. But let's try this out. Notice it's kind of the same as the last problem. We have a constant and then minus the variable squared. fits into this expression, but it's actually kind of a different problem in the sense that it's now not a definite integral. We're finding an overall antiderivative, and that means we are forced to undo the substitutions on this one. So undoing a trig substitution has its own technique. Let's carefully work through this one and see how it goes. First thing to observe again is we're in row 1 on this table right here. So we form out this equation, x equals a sine theta. The value of a came from where we had a squared, which is the 25 in our problem. All we do is we take the square root to get the 5. If it was 23, we would just write square root 23 over here, in other words. So x equals 5 sine theta. That's going to handle x squared down below. We'll just call it 25 sine squared theta when we get to it. But we now have a differential dx. Dx is going to be equal to 5 cosine theta d theta. This is a little bit different from u substitution right at this stage. In this context, we do not divide by that 5. And the reason is we're doing a full replacement of whatever dx is. So whatever is here, we just drop it right in. So in other words, do not divide by 5 in this context, the context of trigonometric substitution. So we've got that portion handled. If we can say what this is, our work is done. Well, I mean, it's not done, but the substitution can proceed to the next step. So let's work with root 25 minus x squared. The way we pick this value 5, again, this is a trick from the table, or from here, we're just taking the square root. But another way to think about it is, we're trying to put a value inside here. 5 is only the one that works, so that when we square it, 25 has to come up again in order for us to simplify. So this is turning into square root 25 minus the square of x is going to be 25 sine squared theta. Now, the next interesting thing you can do with the square root is you can do some nice factoring. 25 appears in both terms, so you can factor out the square root of 25 just outright, algebraically, and this will qualify. Leaves behind 1 minus sine squared theta, which then brings our cosine squared into the picture. So this now is equal to 5 root cosine squared theta, and I'm just going to take a shortcut here. You don't have to write down the absolute value every time, because we now know that domains are targeted to drop absolute value. Cosine is just positive on this domain. So all we get is 5 cosine theta. And so all of that plugs right back into the yellow portion here. That means we're on our way with this, folks. So always, it's kind of a 3-step process. Step 1, pick the substitution. Step 2, do its differential. And step 3, re-express the portion of the integrand, which is the whole reason you came to trigonometric substitution. Simplify the square root portion in this case. After you've done all that, now we're doing the massive technique of dropping things in where we see them. So more substitutions. 5 cosine theta goes here. Divide by the root of x squared. It's not fair to say all of math is substitutions, but when you're doing this content in chapter 2, it really feels like it, because that's essentially all we're doing. X squared means square that, so 25. Sine squared theta would go there. Again, the multiplication here is just my organization to say I'm putting in the portion for dx, which through this differential is just 5 cosine theta d theta. So now we're back to section 7.2 on this one. If we can integrate this, we're well on our way. First, notice the constants cancel. We have 25 divided by 25, and it's just now cosine squared divided by sine squared. So integrate cosine squared theta divided by sine squared theta. I would never want to integrate it in this format because the powers are even. That's usually not great for us. Let's just change the function. This is cotangent squared. Theta, d theta. Now we need to use that related technique we mentioned before of just change this into something else. It's not quite this identity, but if you change this identity by going cosecant squared theta minus 1 equals cotangent squared theta, you've got the right identity. So the idea was change everything from the function to the cofunction, and you now have a true identity. So this is antiderivative of cosecant squared theta minus 1 d theta. Any questions, folks, to this stage? Okay, well, we can get an antiderivative of cosecant squared. That one turns into a negative cotangent. So negative cotangent goes here. That's because, oh, hang on, not squared. Let me try again. That's because the derivative of cotangent alone is negative cosecant squared. We want it positive, so we just throw in an extra negative sign. This one's not as bad. This will just be negative theta plus a constant. And this is a great answer, but we still have a good amount of work to do beyond this point. If this was, say, for example, a 10-point exam 1 question, we could lose between maybe 2 to 3 points by failing to do the next steps. So undoing the substitution is actually a big part of this problem here. The way we do it is we go right back up to the initial substitution that was given, solve for the sine function. So let's just rewrite this down here for a paper trail. X was 5 sine theta. So we now rewrite this as sine theta is x divided by 5. Now, because we are using right triangle trigonometry, a good idea here is just to write down, if this mnemonic is helpful, SOHCAHTOA. The way it's relevant to us is S right here is referring to sine in the SOHCAHTOA. The O is the opposite side of the angle. H is the hypotenuse in the right triangle. So if we come back over here, we're saying that X is the opposite side and 5 is the hypotenuse in our right triangle we're about to build. Turns out I always draw them this way, so I'm not too concerned. I'm just going to say it's a right triangle, even though this one looks like it could be something like 95 degrees. Let's just say it's a right angle. I almost always just put the angle measurement theta here. Then come back up to this. Opposite of theta is x. So that means x goes into this location. So the furthest part away, that's not the hypotenuse. Hypotenuse 5 is the longest side. And now we have a missing side down below right here. There's a trick to this, though. You can either use, let's see, Pythagorean's theorem, but if we were doing everything right and we didn't make a single mistake, that right here should go down here. 25 minus x squared should just emerge as the missing side. Let's check that out through Pythagorean's theorem. If you square this, you would get 25 minus x squared plus x squared. That would give you back the side 5. Or if you're visualizing it this way, you would say 5 squared equals x squared plus the square of that But when you square all this, you get 25 equals x squared plus 25 minus x squared. And that checks as true. X squared cancels out. So that tells us this really was a right quantity. You don't have to do the Pythagorean's identity or theorem right here. It's more of just an internal check. If I drop this from the integral down here, and Pythagorean's theorem checks as true, we have a lot of consistency, great numerical evidence, no mistake was made. Not a guarantee, but it'd be an odd coincidence to make a big mistake and have this consistent. So here's how it helps us finally. Cotangent is the reciprocal of the tangent function. If we wrote down tangent of theta right here, it tells us it will be the opposite x divide by the adjacent, root 25 minus x squared. So tangent theta per this diagram is just this. But that says you can go over to cotangent. It's a reciprocal function, so you just literally take the reciprocal of tangent right there. So we now have an expression for cotangent. Come back over here, it's negative root 25 minus x squared divide by x. Again, just the reciprocal of this over here. Next up is negative theta. This one's different. The right triangle is not going to help us on this one at all, but we still have some really good options. Anyone recall how to solve for a theta to undo that variable there? Sorry, say again. Yeah, absolutely. So the idea here is, because this is an inverse substitution, if you're undoing it, you literally need the inverse function for sine. So let's write it down here. I need way more space than I thought. Let's just push that problem down. If sine theta is equal to x over 5, then this implies either arc sine or sine inverse. Let's go with the arc sine since you mentioned it. Arc sine of theta is, or excuse me, let me try again. Theta would be equal to arc sine of x over 5, as you said. Or you could put sine inverse here as a different way. I like the arc sine function because there is no misinterpretation of what the negative one is. It's not an exponent for sine inverse. So back over here, go arc sine x over 5 and plus a constant. At this stage, we've got it, folks. This is trigonometric substitution when you're dealing with an indefinite integral like this one here. It has this annoying portion of the SOHCAHTOA steps, if you use that method, or the right triangle, to undo the substitutions. Does that stage make sense to folks on getting cotangent re-expressed and theta re-expressed? Okay, and again, like I mentioned, there is a lot of ways to do these problems sometimes. A U substitution might work, but again, you have to be take a lot of ingenuity on this. The way it could work is, we go back to section 7.1, we solved a particularly weird problem, but it did have a purpose. Here it is. Let's go to the very bottom of these notes. And at the very bottom of these notes, we were solving cosine root x. It was a weird problem. We used u equals root x to get through it, but we made the integral a little bit worse. But notice what we did over here. We rearranged the differential. We brought u back inside of it, and that's what allowed it to eventually work as an integration by parts problem. So that's what sometimes can happen here. If you do a u substitution just right and do a lot of algebraic surgery to your differential, it could potentially work on these kind of problems. So if you like that approach, I'd say go for it. But I'd still encourage you to try this out because at least it is a direct path to a solution where you don't have to worry about what to try in a u substitution, where there are many, many options out of nowhere. But let's see where we're at so far. Next one is going to be a variable minus a constant. What this reminds me of is an identity that goes secant theta minus 1 equals, excuse me, those should be power 2 equals tangent squared theta. So if that's the case, it looks like this one right here might be a secant for this substitution. But really probably the better way to think about it is, this is a fantastic table. We should just use it for all it's worth. That's what it's here for. Much like the periodic table over here, I don't know if you can see it on Zoom. Without these kinds of things to help us organize the information, the problems are harder than they were ever intended to be. So let's just use this again. So if you have the variable coming in first, subtract a constant, you should be using the secant identity here. And this is the related identity that comes up. But looking at the time we've got, I have about 6 minutes and or 7 minutes to work through this one. I think this one is going to be a good one for us to come back to because I think this is quite a bit of a longer problem to get through. So we'll come back and solve the last problems on these notes here when we're a little bit more fresh on Monday's class, and then segue into section 7.4 potentially as well on Monday. But any last questions or comments at all, folks, before we call it a night officially? Good call, absolutely. This one's actually pretty tricky. That's the reason I wanted to spend more time. Because if you did start right here, you would go x equals, from this position, definitely a 2, secant squared, or excuse me, secant theta. But if you threw that in, the 9 doesn't go away. So we just divide by the root of it, exactly as you said. So yep, that's how we're going to be able to get through this one here. Other questions about this one? Okay, well, we'll come back to this when we're a little bit more fresh on Tuesday's class. Looks like I have just a couple more to get through. This one looks worse than it really is. Then we'll be in the next section, 7.4. But have a great weekend, folks. If you do have questions that come up, please don't hesitate to write. I'll be happy to work with you on those. Thank you, sir.
Quick question.
Sure.
So I was doing section
Yeah.
7.3. Does it all right to you?
Let me take a look here. So x squared minus 9. So you want a secant on that, 3 secant theta. 3 secant theta tangent theta. So you got that in there. 27. Then this one should turn into something like, looks like
A 3.
3 tangent theta. Yeah, looks good there. So you had 3 tangent squared. That looks good. The secant cubed, so down to secant squared.
And then I got rid of the 3 and the 3 here. So then that
Yeah.
turned into
This looks like it's on the right track. We're left with a tangent secant, tangent squared, so sine, that goes to cosine. So you're just doing this reduction formula. Yeah, I think you've got it on this one. This is
Okay.
a great approach.
well, because you gave a hint to 19 that said use the double angle.
Oh, that's right. I
Zero.
think I do remember that coming up.
And I didn't see how.
You know, I think I used this when I was undoing the substitution. So when it goes to the right
Oh.
triangle, it'll come up there potentially.
Oh, okay. Yeah, no, 'cause I was like, I don't know where the double angle theorem even came into play with this one. That I was
Gotcha.
doing it, and it was just throwing me off, 'cause it was like, I don't know.
Yeah, so let me take a look at that just one more time. So it was 3 secant theta. And so you had theta there. You know, now I'm looking at that, I'm not too sure why I had that hint. Let me take a look at my own work on this. So I've got it.
Oh, sorry.
Here, no worries. 7.3, number 19. So I came out with a tangent squared, secant squared, sine squared reduction formula. And then, oh, here's the issue. On the reduction formula, I forgot this part. You get a cosine 2 theta, comes out as a sine 2 theta, but you actually can't use sine 2 theta on your right
Oh,
triangle.
when you're going back?
Yeah, you want to break
Oh.
this up into that thing, so then your right triangle is
So then
valid.
that could work. Oh,
Yeah.
okay. That makes
It's
way more
really
sense.
subtle thing right there on that last part.
Yeah. Well, because I figured maybe you could do it like where you just plug it back in. cause I forgot to put back the two theta right
Yeah, I
here.
missed that part too, and I was looking over your work from the reduction formula is where that side effect came into play.
Okay, no, thank you.
Yep,
That was
absolutely.
really throwing me off. Also, yeah, I was treating these like how you would treat a U sub where you could, cause I always divided by or multiplied by whatever your du or your d theta would be. And it was-
How do you mean by dividing?
So like on a U sub, you know
Yeah.
how, like, let's say we wanted to U sub this, the x squared plus 9 minus 9, we would say let u equal this, du would equal 2x.
Oh, you mean dividing?
And
out
then
the
dividing
two.
out
Oh,
the 2x.
gotcha.
Yeah, and I didn't know you couldn't do that with like these.
Yeah, it's all because you're replacing the whole dx, so whatever your du is, just gets totally written in with no divisions.
Okay, well, thank you.
Yep, absolutely. They're definitely weirder kind of substitutions.
Sorry, I'm like going ahead. It's just like my like my social medias and everything are just math now.
Oh, yeah, that's kind of cool.
Yeah, so
I think
now
it's survival too sometimes. You gotta work ahead and just in case something happens at
well,
the
that's my
project
thought
or so.
process. Like, I'll try to be like a week or two ahead. So sometimes when I don't feel like doing homework, it's given you.
Yeah, you've got a period to recover at that point, yeah.
Like, see, this is my feed. It's nothing but.
That's kind of cool. Yeah, the more you get your head in that headspace, the easier all this is to get through for sure. That's a great strategy.
Do you show the formula for partial fraction decomp?
I do, yeah. It's gonna come in as the all case 1 through case 4, so all those little parts.
I know it changes if you have like an x squared. If it doesn't reduce nicely.
Yeah, that's gonna be our case 3, I think, ours, our author calls it.
All right.
Also for repeated factors, we'll have different cases for all that stuff as
All
well.
right, yeah, it's like what would be like a good example?
Like 1
Like
over
an
x
x squared
cubed,
plus 2 squared or something like that,
x squared plus,
2 and then cubed.
yeah, something like that. That'd be a repeated irreducible factor. That's now case 4 in our theorem.
Okay, well, thank you.
Yep. Have a great weekend.